Perfect. Hello, everyone. My name is Rahim, and today I'm going to talk about fast video generation. Thank you for joining, and thank you, Olga, for the nice introduction. So I'm going to talk about some of the recent state of the art. I would say recent up until maybe 3-4 months ago. The problem, the community is very fast moving. So I'm going to cover a couple of papers. Please jump in if you have any questions. Either in the chat or just unmute and ask me. Okay, so why fast video generation is needed? Because as you can see in this plot, slow video generation or conventional video generation is very, very slow. So here you can see different one models. One is one of the best open source models out there for text to video and image to video generations. And you can see different versions like here on different resolutions, different sizes. And like this one, which is about maybe more than 6 months ago or a year ago, 2.1 text to video 14B. I guess it's about 1 year old, which take about 1 hour to generate only 5-second video on a single GPU, which is drastically long. We don't want to generate 5-second video in about 1 hour. And this is, and of course, the smaller the model, it will be much faster. And there is also 2.2 models recently. I guess it's about 4 or 5 months ago, but this is also very slow. So that's why we need, from the practical perspective, we need much faster video generations because users are not patient enough for that. Not only this, but also this is very important for interactive video generation, because most of the applications out there, like in filmmaking, professional filmmaking, you may consider like Hollywood video generation or self-driving cars, there will be a lot of interactions with the world. So you want to interact with the video. You cannot wait for 1 hour and then the next video generations. That's why you need to make this much, much faster. So I just put up a link here from a recent paper, long live. And if I just want to open this, I guess they have a very nice demo. So you can see here a video is generated. This is a slow video generation for 5 seconds. This is going to take some time, but then they make it much faster so that you can interact with the video. So as you can see, you can type in some prompts and new events are generated as if that you are interacting with the video through prompts. So this is not going to take 1 hour. This is like real-time video generation on single GPU. So hopefully by the end of this talk, you have some clues, at least some ideas how this is going to be happening on single GPU. So there are different dimensions to make this efficiency possible. Some of the most important ones are making the video generation autoregressive. So from pure diffusion, conventional standard diffusion, to make it autoregressive diffusion generation. Also a sparse or efficient attention mechanism. Distillation is also very important. Not only this, but also there are also methods like feature caching, fuse kernels, quantizations, and maybe some more. I am gonna try to cover some of these, especially autoregressive distillation and sparse attentions. If we have time, maybe I can show you some other tricks too. Let me begin with standard video diffusion to make sure that we are all on the same page. So standard diffusion starts from reading a data points, adding noise, so that up until we have full pure noise, which we call forward diffusion process. And then in the reverse diffusion process, we are going to denoise this step by step. This is a standard diffusion process, which is actually in 2 steps. And the magic of diffusion is actually denoising. So for adding noise, we can just combine, write like simple formula, adding Gaussian noise up until we have full noise. But then we train a neural network, which job is actually to denoise this, because this is quite a very hard task. How we can get from this step, which is pure noise, to 1 step less noisy, so on and so forth. From image diffusion to video diffusion, this is a schematic from 2.1. And as you can see, we load some data points. So instead of just one image, we have few images as frames of a video. Of course, we want to encode them. I'm going to show you in the next slide why is that important. But assume that instead of working on full resolutions, we are working on much less number of tokens. We add noise, as we did for the previous slide, and we do diffusion process, which is multiple times. Let's say while doing inference, we do this 50 times or less. So we add noise. And then the DIT blocks, diffusion transformer blocks jobs is actually to denoise this. And of course, we can use some cross attention through some texts. For example, here we use offline T5 encoder to cross attention through these DIT blocks, so that if you want to add noise and then denoise, we just guide them how this denoising process should be done with respect to the text. And then after this diffusion process is done for many steps, during training 1000 steps or during inference 50 or less, then we decode it again back to full resolution, like in pixel space. So this is the full schematic of one video diffusion process. And this is the VAE, the encoding process. So let me explain first what it does. It starts from like an input video, which is have T frames, let's say 80 frames, like 5 seconds, 16 FPS. There is some height and width, let's say 1000 by 1000, and then 3 channels. That's the input video. The job of this VAE is to compress and decompress. This is variational autoencoder. So this is trained by different loss functions like reconstruction loss or KL on top. And the job is to actually make this much smaller, so that this bottleneck, this latent space, is much smaller, easier to train, and hopefully it's much better to train in the next step, which is actually the diffusion process. So if you may recall, we have this VAE encoder and decoder, and this is the encoder and the decoder here zoomed in. So the one VAE 2.1 has temporal compression of 4. So instead of like 80 frames, we have now divided by 4, 20 frames, and then division of like 8 times compression towards heights and widths. So in total, we have 256, 64 here multiplied by 4, which is 256 times smaller. And then there is some channel. So we had, So we had 3 here in 2.1, if I'm not mistaken, it is 16. So the compression is 256 divided by 16 multiplied by 3, which is about like 100 or less than 100. So now this latent space is much smaller than the pixel space. In theory, we can work on pixel space, so we can remove this decoding and encoding and decoding, just add noise to the pixel space, as I shown in the first slide. We can add noise and denoise. But there are some works like latent diffusion models that showed that it is better to do this on latent space because of mainly 2 reasons. It's much simpler, it's much faster, and you can do larger scale. And hopefully the VAE is also transforming your features into a space that it is easier for the word model, for the generative diffusion models to actually learn those temporal and spatial consistencies. So throughout this talk, I want to demystify actually the video diffusion process. So don't be afraid if there are some formulas, there are some numbers. I just want to give you the impression throughout the talk that this is not a black box, and this is actually much easier than you think. So what happens in the diffusion pipeline? So I'm going to show you what is going on in this black box of diffusion process. So what we do is to, as I mentioned, to encode. So let's say we have 80 frames, 256 by 256 pixels. And because we have 4 by 8 by 8 compression, so 80 will become like 20, 256 will become 32, and then again 32. So now we have this latent. We add noise to this, which is like a standard Gaussian noise added. And then once this is ready, then we do like 3D conv to make it ready for the DIT diffusion, like transformer blocks. 3D conv is like simple like very simple and similar to 2D kind of convolutionals. Instead of 2D, we have now temporal convolutions. So they have like 3Ds. So remember, we have this VAE output. Now we have 16 channels, 20 frames, 32 pixels as height and width. Now we get this given to 3D conv, and the output will be like this. Why? Because very easy formula. If you want to get the output of CNN, then you have the input minus kernel divided by stride plus 1. So for example, if you have like 20, for example, if this is 20 by 32 by 32, for example, 32, which is input, minus kernel, which is 2, 32 minus 2, which is 30, divided by stride, which is again 2. So 30 divided by 2, which is 15, plus 1 is 16. So I just made one example how this magic number is coming. So that's very easy. You can do this manually from here to here by 3D conv. Now the input is ready. We just need to flatten the token because transformers like these flattened tokens. So you have the dimension, which is 1536. That's the dimension of 3D conv. That's pre-assigned. You design, this is a design choice. So you have 1536, 20, 16 by 16. You just flatten this. The dimension is still 1536. Like multiplications of these three numbers is 5120. And now this is ready to go to the transformer block. I'm going to give you more details what is inside the transformer block, but assume this as a black box for now. Then after the diffusion process happening, so through many times, then we do the reverse. So we have the unpatchification and then the VAE decoding as I shown here. So we had this encoder, we have this diffusion process, and then the decoder. Any questions? If not, then we go to the next one. So what is going on inside this step 5, the transformer block again? So the transformer block has mainly like 6 different steps or 4 or 5 different steps. The first one is pre-normalization. So we have like normalization layers. Then we have QKV projections, which is actually you have this, remember from the previous slide. Then you like normalize and then modulations. This is QKV projection. So you have batch sequence head dimensions. Then we apply rope embedding, or you apply another positional embedding. In this case, in one, you apply rope embedding, which is, so if you don't have backgrounds, so in diffusion process or in transformer process, when you have an image and you want to patchify it, so you have a sequence length flattened, remember? So this is the sequence length flattened. Now I want to know which patch or which token is correspond to which part of the image, right? Because if this is top left and another one is second row top left, we want to make them close enough so that the transformer knows that they are connected to each other. That's why we use some sort of positional embedding. So we don't want to lose this information. One way to apply positional embedding is 3D ropes. Ropes and then 3D rope, because we have now 3D data, 20 frames by 16 by 16 special patches. Then we do the attention mechanism. So probably most of you, if not all, knows about how the attention works. So I don't deep dive into the attention, but let's assume that attention is just finding out of these different, out of this sequence, which of them are connected to which. So I created this sequence. So this is the sequence length out of these 5,000 tokens, which are flattened in a row, which tokens are connected to which tokens. This is the magic of the attention. And then ultimately we have some output, and then we are going to visualize that output. There is one question in the chat. In the diffusion video architecture, do we use residual connections? I guess we do. Yes, we do. I don't have the figure here. Yes, but we do residual connections too. Yeah, if you look up like stable diffusion paper or one, you could see the residual connections too. For most of what we are doing here, I don't deep dive into the architecture itself. Your question is about the architecture of the DIT blocks. I do mostly the surgery or the understanding of the diffusion process itself. So just to wrap up, we had this attention mechanism. So we had some frames. We make them into VAE, so we decode them. Now we add noise, and then the DIT blocks is to denoise it, and then ultimately we have the output. So this is just one frame, adding noise, denoise, and then again, same frame. And hopefully these two are similar to each other when we train the diffusion model. So I'm going to talk about three distinct sections. So what I just talked about is an intro to diffusion. But from now on, I want to make this fast video generation. The first step is from standard diffusion to autoregressive. So the goal for this stage is to take a pre-trained video diffusion model, like 2.1, which is standard diffusion, which is very slow. It takes 1 hour to generate 5-second video, and try to make it fast enough and causal and autoregressive. Why? Because in a standard diffusion model, so I guess this is a good figure to refer to. In a standard diffusion model, we take all frames, let's say 80 frames for 5 seconds. And then for each of these frames, we encode them, add noise, and then decode. So you can imagine that these 80 frames need to be added noise and then denoise at the same time in parallel, but all of them should be ready at the same time. So this is the main bottleneck of diffusion. So you need to wait all the frames to be ready so that you have a video. What you can do instead is to generate autoregressively. So start from this frame, generate, and then fed it back, next frame, and then fed it back, show to the users while they are watching this frame, then the next one, so on and so forth, right? So this is the main objective of this section. We want to take a diffusion process, which is parallel, but slow, and then make it autoregressive, so which is block causal attention, and then make it much faster. So the bottom line is take a bidirectional diffusion transformer and make it causal autoregressive. What do I mean by causal autoregressive? So imagine a very simple example. So we have only 3 frames, 2 tokens in height and 2 tokens in width. So we flatten, as I showed in the previous slide. So we have 3 multiplied by 2 by 2, there will be 12 tokens. So these 12 tokens here are ready to go into the diffusion transformer, right? So we have batch sequence heights and the number of dimensions and so on for Q and K, and then we do the attention score. So if you're familiar with applying attention, which probably most of you are, then the PyTorch supports a mask. So it says that I can support causal attention, which means that if I want to do causal attention, you don't look for the future. So imagine a full causal attention here. So here are the 12 tokens here, and here are the 12 tokens here. Remember, the job of attention is actually to look which token is corresponding to which token, how much this token is connected to this token. These two are fully connected, right? Because this is actually the same token. And then this one to this one, and this one to this one, right? So imagine like an image which some birds are flying. So there is a correlation between pixels of the bird's bear, for example, but there is less correlation between birds and the ground. There is still some correlation, right? But there is not as high as possible as like the bird's pixels to each other. So by default, PyTorch supports the causal attention, which says that for this token, don't look at the future tokens. So wherever there is one, which means that don't look. So this is by default, one line of PyTorch. So you say that triangular matrix, and then there is ones, and then by the sequence length, which is 12, and then you just apply this, you create this mask, and then you give it here. So wherever the mask is 0, then make it 1 to the power of -9. So it says that when I'm looking at this token, when I'm processing this token, don't look at future tokens. When I'm processing this token, only look at this one and whatever comes before that. Don't look at the future, so on and so forth. So for the last token, which is probably the bottom right token, it matters have you scattered the image, but scan the image. But assume that this is the bottom right token. So if you process this token, you can look at all tokens before that, which is basically all the tokens, and there is no future token, right? So this is very simple view on causal masking. But the problem is that for video or like an image masking, this is not true, because when you have, so what are these tokens? This is, assume that these are the tokens from one image, right? So this is the first token. This is the first token, top left, let's assume. And then the next token, And these are 4 frames. These are the 4 tokens from a single image. Remember 2x2 patches. So imagine, I should have had a better picture, sorry. So remember, this is like a rectangle with 4 different sub-elements. And we have 3 frames. So each frame has 2x2. Now, these 4 tokens, so from F0, which is frame 0, all of them are frame 0, and different patches. Patch 0, patch 1, patch 2, patch 3. So these are all patches from the same frame. Right? So the problem is that if you do this patch, which is actually from the same frame, this is patch 3 from frame 0, does not correlate or does not attend to the same frame but different patch, which is not true, right? So we want an image spatially correlated and attended to all of the patches in the same image. But we want to do this across frames. So what we do instead is that now all of the patches in the same frame are attending to each other. Remember, if there is 0, it means that mask is 0 and the attention should be applied. Now, this patch here can attend to this one can attend to this one, so on and so forth. So now all of these 16 elements, sub-elements, which are, these are different patches from the same frame, can attend to each other, and so on and so forth, right? And this is, again, very easy, not one line of the PyTorch, but through a for loop, you can create this mask, and then again, fed this mask to this function here. Yeah, so you create a mask, and you just fed it to attention scores.
So the 4x4 patch that you took is for a video, and the 1x4 patch is for the image.
Yeah. So now we say that these are the 4 patches from the same image. These are 4 the patches from the same image. Now I want to especially say that these are now connected to each other. They need to attend to each other. But then when I go here, I want to look at the previous frame, right? This is the previous frame, but don't look at the next frame. Yeah. So when I'm in the first frame, don't look at the future frames. But then when you are in the second frame, you can look at the same frame and the previous frame, but don't look at the future frame.
Oh.
Does this make sense?
Yep. Thanks.
Cool. No worries. So now you can do this in a for loop or easily with one line, vectorized. So this is still possible with one line of code in PyTorch. Now you have this mask, and then you say that, yeah, so once the mask is ready, then you get it to the attention score, and then you get the attention with respect to video masking, right? So now we could support the causal future masking, which is the first step for making autoregressive, the most important step, I would say. Now, just to wrap up, what I did so far is to take one, which is non-causal, which means that when you do attention, so here, when you do attention, you do look at all of the frames, right? So you all of the tokens look at each other. So imagine all of this is 0. So this is what happens inside of one, non-causal. When you create this, 80 frames, all of the frames can attend to each other. From previous, from future, this is why it is non-causal. Now what we did is to take this non-causal attention, make it causal. That's the first important step. And now let's train it. So there are two steps. You can now apply this causal, load these pre-trained checkpoints, then do the surgery, make this causal attention, and then fine-tune, which is called diffusion adaptation. And then there is another step, distillation, which I'm going to give you more details in a few seconds. So in diffusion adaptation, there is actually two options, sub-options. You can do no distillation, which is very straightforward, right? So you take the base model, make the surgery with causal attention masking, and then fine-tune on your data set. This is like CVID APT2 from ByteDance paper. There is no distillation. Or some of the recent works like self-forcing and CauseWidth are from the same group. They combine this with time-stamp distillation to even make it much faster. So distillation is not part of the diffusion adaptation. You can fine-tune without any distillation, but people found that it is much easier or even better to combine the autoregressive part, the causal fine-tuning, and the distillation. Distillation means that instead of 50 steps, now I want to do this in 4 steps, which makes it 12 times faster, right? Any questions for now? Okay, cool, Olga. We can talk about the questions later. So training, let's go to the distillation. So the first step was very straightforward, right? So I don't have many more slides for the first one. You take the one, make it causal, fine-tune it now with the surgery. So that's very straightforward as you did. Assuming that you know how to train diffusion models, this is exactly the same. The only difference is that one line of the code, you just give the transformer model or the attention in PyTorch or Flash attention, like the mask. Now I want to give you more details about the distillation. That's the second. So the first step to make fast video generation was to make it autoregressive. Now, instead of waiting for all 80 frames, you can generate only few frames and then few frames and then so on and so forth. For example, in one, we have 21 latents multiplied by 4 because 4 times compression, then it is 80 frames. In 21, we can do causal block attention, which is 7 blocks, each of which 3 latents. So you generate 3 latents, then the next 3, so on and so forth. So now when the next 3 frames, 3 latents are generated, the next 12 frames are actually generated. So instead of waiting for all 80 frames to be ready, you generate 12 frames, so on and so forth. Okay, so that's the first way to make one faster by dividing into multiple steps. And the second step, which I'm going to cover next, is to make it distilled, which makes it time-step distillation, which instead of waiting for 50 steps, if you may recall this iterative process of diffusion models, we do this multiple times. So we just add noise, denoise, again, add noise, denoise, so on and so forth. We can do this in 50 steps, or when you do distillation, you can do this in 4 steps, or even in single step, which is 50 times faster. How does distillation work? So there are different ways to make distillation. One way to do that is DMD. It is one of the best ways. Most of recent works in video diffusion models are using DMD, distribution matching. That's why I'm going to cover this here. This is a bit noisy slide, like there are lots of details here. I'm going to go over some of these details here, like step by step. So the main objective of distillation is to, if you may recall from standard machine learning, there is like teacher-student regime for distillation, right? So we have a model, which we call it one-step generator, which is few step generation. So this is the student. And there is also a real score, which is the full step diffusion. So imagine we have a copy of the model, which generates images or videos, in this case, images in 50 steps. There is another copy which does this in 1 step or in 4 steps, which is much faster, which we call it the student. And we want to train them together so that the student is, by the end of the training, a student is good enough to mimic the distribution of the teacher. That's why it's called distribution matching. How does this work? So we start from a random latent. We generate something. Of course, this will, we denoise it, right? This is the job of the one-step generator or few-step generator. We denoise it. So in this, assume that there are many noisy pixels here. And then this is not good enough, right? So you just add noise and then denoise. So you have fake score and then real score. This is the student. This is the teacher. So you ask both models to denoise this. So you add noise, then denoise 2 times. One denoise it perfectly, hopefully, because this is very good, already trained. This is the teacher model, denoise it like this. The other one tries to denoise it. There will be some noise here, like not some Gaussian noise, some artifacts. So this is not as good as this one. Then you get the difference between them, and then you backpropagate this gradient to the student model. That's loss number 1. There is also loss number 2, which is diffusion loss. So if you do only this part, so you add noise and then denoise without using the teacher, this is the standard diffusion loss, right? So you can, if you may recall from the very first slide, the diffusion process adding noise and then denoising. The denoising process, the reverse denoising process, is training a neural network with some loss. And this is the diffusion standard loss, right? So this is loss number 2. So you just do standard diffusion loss. This is loss number 2. And there are some auxiliary losses that people found that they are useful, like regression loss between generations, between this one generations and a paired data set. So you generate offline a very good ground truth, and then you compare the distribution, the differences between these generations and this offline loss. This is not very important. So this is covered in recent papers like DMG2 or some other papers, but the basic idea is to have a teacher, to have a student, and then train them hand to hand at the same time, so that by the end of the training, the student is able to mimic the distribution of the teacher. Okay, so that's what I want to take from this slide. The DMD matching is to train teacher and student together so that the student can mimic the distribution of the teacher. And these are some losses. It's not important why these losses are fed into. This is just more or less surgeries. This one should be like gradients, and there are some tricks to make this work. I'm going to skip this because this is too much details. And now assume that we want to train, right? So remember, now we want to distill, and now we want to train the distilled model. So these 2 or 3 slides are coming from self-forcing paper or COSVIT, both are the same. So the first step is to take the diffusion, the teacher model, generate a lot of samples. And there is no student yet, right? So you for example, in self-forcing, this is called ODE solution pairs, ordinary differential equation solution pairs. So basically what you do is start to generate 16,000 videos. You have 16,000 prompts, let's say, right? And then you take the base 1 model, teacher model, which does 50 steps, no distillation yet. And then you generate a lot of videos, like 16Ks. What you do is that you save this denoising process, which we call ODE trajectory. So if you have a clean video, you add noise and then denoise. Then if you add noise without any denoising, then you save this one. If you add noise and then denoise it for 750, denoise it for 500, and then denoise it for, or add noising for 250 steps. So you can just save this as a matrix on the hard disk, right? So now you have generated 60K solutions, 60K videos, which are clean videos. Not only this, but you know what would be this video if I want to add 250 steps of noise, 500 steps of the noise. Why do I want to save this? You'll see in the next slide. So that's straightforward, right? So now I have this matrix. I have 21 latents, 16 channels. This is heights and widths. And then you have 5 because you saved 5 different versions of the same video. Clean, 250 up until 1000. This is pure noise. Hopefully this is pure noise. Less noisy up until it is cleaned. That's why we have this. Now, the second step is to use regression using these pairs. So this is what's in the previous slide, right? So you want to train and then denoise. And then I'm going to give you more details how this is trained actually using this teacher and student. So remember this causal one. This is a pseudocode, right? So remember this causal one. Now I made causal, and now I want to train it using distillation. I have access to the ODE pairs, which are these 5 timestamps. So we ask this causal one model. I give you a noisy step. So I randomly select one out of these 5. Let's say I chose these 250 steps. So there is a generation which is added 250 steps, slightly noised up. And then we ask this causal one model that I created, let's denoise it. It generates some videos. It tries to denoise it. And then we get the difference between the MSE between the grand truth, which is clean, right? This clean, and whatever this causal one generated. And we call it the loss, right? So the distillation part is, that's why here, if you may recall, they combine this with a time-step distillation. Now this is the combination. So you just generate this matrix and then try to do MSE regression over grand truths, which are clean, generated, and slightly noise and then denoise using causal one. Cool. Let me have a look. I'm gonna also cover slightly these slides, just at least high level. So I covered this parallel standard diffusion. And then there are different other methods to train a standard, to train a diffusion model. If you may heard of teacher forcing, diffusion forcing, or student forcing. I try to make this as high level as possible. So remember the QKV from the transformer model. In standard diffusion, we want to, we are at Q, the current frame, and then tokens are noised, and then want to denoise it. And when we want to do the attention between Q and KV, we say that all the frames at the same diffusion levels are needed to denoise. When a standard diffusion, we have access to the previous and then the next frames, right? This is a standard diffusion. In comparison, teacher forcing, for example, all of the Qs are same together. So now we are at some steps. This is the Q. We want to add noise, right? So there is a random noise added. And when we want to denoise, let's compare teacher forcing with the standard diffusion. So in a standard diffusion, we have access to all previous and forward frames, added noise, right? So, but in teacher forcing, we have access to the grand truth without noise. So the difference between teacher forcing and the standard diffusion is the KVs. The KVs for standard diffusion is that now if I want to denoise here, so I'm here, added noise, I want to denoise this, right? So this is added noise. I want to denoise this so that I have this. How can I do this? This is the Q, and KVs are coming from the previous frames. But these KVs are noisy, right? Because this is already noised up. If I want to denoise this one, I look, give me the KV, and the KVs are noised. However, for the teacher forcing, I'm here, added noise. I want to denoise, and then I ask the previous ones if this is causal, and the previous ones are not noisy. That's why it's called teacher forcing. Why this is helpful? Because when you want to denoise, there is actually clean context, clean KVs. This is much easier to solve than this one, right? So for people found out, and many papers are using teacher forcing, at least earlier in the like distillation or standard diffusion or diffusion training, because it's much easier to train. When I want to denoise, I know what this frame was. I know what previous frame was without any noise. But here, if I want to denoise, I have access to the previous frame, which is good, but this previous frame is also noisy. You see, this is a much harder problem than this one. The problem with teacher forcing is actually while doing test inference, you don't have access to the previous clean. That's why we have something like self-forcing. Let's have a quick look at self-forcing. So self-forcing Q is coming from the same, again, same. But the difference is that now we want to use the generated previous block. That's called this rollout history. That's very close to LLM autoregression, right? So the main objective, the problem with teacher forcing was that we have a hint, we have a cheat sheet, right? So we know that the previous frame was clean and we used it for denoising, which is great while training. But the problem is that while doing inference, we want to denoise this and we don't have access to the previous previous clean, right? We generated something. We don't know if this is good or not. That's why we used self-forcing also in training. So in training, we want to denoise. And then when we want to denoise, we use whatever was generated. So this is the loaded from training data set, loading from training set. But here it is loaded from the generation. So whatever is noided, that there should be an arrow here. So whatever I'm here, added noise, want to denoise, give me the context, give me the KV, and this KV, this arrow should be from here. So it should be from here to here, gave me the generations, and then go on, and then so on and so forth. The upside is that this is reducing the train test generalization gap, right? So there is a gap between train and test. I want to remove this gap. What I would do is to mimic the test in the training too. That's very common practice also in the standard machine learning, right? So you try to improve generalization. How? By mimicking the test distribution, by mimicking how you would behave in test scenario. And this is why it calls self-forcing. Diffusion forcing lies somewhere between. I'm going to skip the KV caching. And how much time do I have? Maybe another 5 minutes I can use. Cool. So in this slide, I'm going to show you. So whatever I showed here is to take a one model, make it autoregressive by causal attention, simply few lines of PyTorch, and then train it either without distillation or combined with distillation, so on. We also take a look at diffusion forcing and like teacher forcing and self-forcing, which reduces the gap, which gives us better results. So of course you can do also always a standard diffusion, but these are the tricks to make your video generation even better statistically. And then in this one, I want to show you how people generate long videos. So one way to generate long videos is to do autoregressive, right? So you can do, that's why LLM can talk forever, right? So you can just generate next frame and then next frame and next frame, right? The problem is that if there is some error, this will be propagated through time. In this few slides, I'm going to cover some heuristics, how we can reduce this error and generate long videos. So one way to do that is to use local attention. So by default, we are enabling global attention. So when we start from, so I'm going to give Olga some of these slides. So don't be afraid if there is too much details or pseudocode here. That's for offline reading. But in global attention, what we do is to, for example, what long-live did on top of one is to train longer sequences. So long, remember, it was trained on like 21 latents. It should be latent instead of frame. So 80 frames, only 5-second videos. They created another data set, which is much longer. That's heuristic number one, which is straightforward. Why not? They use self-forcing that I covered. The next one is short video attention. If you want to do global attention means that, if you may recall from previous slide, if I'm here, look at all previous latents, all previous tokens, right? This is very computationally intensive. What they did, because they couldn't fit this into memory, is to use local attention. So when we are generating this latent, this is the queue, which of the previous KVs should I look at? And they like create a window and they only look at some of them. So for example, 12 latents when I'm generating this frame, this latent, only look at the past 12 frames. And they also used a frame sync. These are some heuristics, right? What is frame sync? Imagine that you generate first frame in a video, and there are some details like like a child biking, for example. If you use frame sync, if you don't use frame sync, you generate something and you forget what it was generated in the first frames because you just use the last 12 and you just go over window, right? So there might be some errors that adds up on the fly if you do autoregressive generation. But if you do frame sync, you use the first three frames, the first 3 frames that you generated fixed. And then you always, when you are far away in the future, you also not only look at the last 12 frames that you generated, but you also look at the first 3 frames too. So there might be some details that you forgot. For example, this is very important in like personal, like face consistency towards frames in video generation. So there might be a child biking, then you generate some bike, and then there was some faces here in the first 3 frames, no face, and then again the face. You want to recall what was the person, right? That's why you sync on the first few frames. Whatever is there will be attended, will be in the attention for the last few frames also. It's always there. Yeah, so there are more ideas. I guess we don't have time for all of them, but I'm gonna skip, but keep them in the slides. Please have a look. I try to keep the codes and like references in the code. Like these are 2 papers, block cascading and rolling forcing. Please take a look. And this is also from fast video sparse attention. The main idea here is you don't have to wait for all the steps to be ready. You can do some parallel computation, which makes the video generation even faster. The main idea here is that recall here, when you wanted to have a look, you can do global attention, all of them, or local fixed attention. The main idea of fast video sparse attention is that which of the previous contexts should I look? So they learn which of these previous tokens are more important, which is a very nice idea. You don't do fixed, you don't do local, global, but you do somewhere between. So you choose, maybe this frame is important, this one is not, this one is not, so on and so forth. That's the main idea of video sparse attention, but this is gonna take some time to explain this idea. Okay, cool. I guess we are done. If you have any questions, please ask.